Here at Wisconsin Autonomous, we're committed to advanced research and development of self-driving vehicles. Today, we'll be giving you a virtual tour of how we're building the next generation of self-driving cars here in the College of Engineering at the University of Wisconsin-Madison. We'll show you the facilities we use and how we've created discrete subteams to focus on each aspect of the autonomous driving task. I'm Alex, and I'll be your guide. Now let's head inside the Engineering Center's building to begin. Engineering student organizations such as Wisconsin Autonomous are one of the best ways to get hands-on, practical experience applying classroom theory to real-world challenges. The automotive teams have a rich history of excellence. Wisconsin Autonomous competes in the International SAE GM Auto Drive Challenge and National EV Grand Prix, with previous competition experience in the International Indy Autonomous Challenge. Here you see one of the electrical benches available for use in the automotive team lounge. The lounge is a shared space to discuss designs and keep computers for the snowmobile, Baja, autonomous, and Formula teams. This is where we keep our Scale RC cars for rapid indoor autonomous testing, our NVIDIA HGX Xavier, and new team desktop with NVIDIA GPUs. Now we'll head downstairs where the vehicles are built. We've implemented special COVID protocols to remain open with limited capacity for most of the past year. Don't forget your safety glasses. To our left is Baja's off-road vehicle bay. Looks like they're out for a drive. To our right is the Bucky Wagon, a 1932 fire engine that's been fully restored with an all-electric powertrain. Here's a look at our work bay with tool chests and storage cabinets behind our go-kart, capable of both manual and autonomous driving. Next up are the Formula teams. They build two 1/3 scale Formula 1 cars, one with a combustion engine, the other with in-hub electric motors, and both with a carbon fiber monocoque chassis. In the back, we have our composites room, where materials can be safely formed and sanded. We have a sanitizing station, and are very fortunate to have a wide variety of high-quality machines and tools. Autonomous vehicles offer great potential for improved transportation safety, efficiency, and ease of use, but are also as challenging as they are new. A symphony of electrical, mechanical, and software systems need to play exactly in harmony for the system to work, but together they can offer more robust, higher-performing driving than the world has ever seen. Our team works closely with sponsors and academic research labs in pursuit of this goal. Our subteams focus on certain aspects of this challenge and include perception, state estimation, driving functions, simulation and software platform, vehicle systems, and operations. Now we'll hear more from those leaders.
I'm Mason. I'm one of the perception leads on Wisconsin Autonomous. If you've ever seen a Tesla driving in autopilot mode, you probably wondered, how is a Tesla able to see the world around it? On campus, we also have these cool autonomous food delivery robots. Perception is the eyes of a self-driving vehicle, except self-driving vehicles don't have eyes like humans do. Instead, they use sensors like camera and LiDAR to see the world in 3D. The most interesting part of perception for an autonomous vehicle is how we use computers to turn a bunch of numbers into something that's actually useful for driving, such as this. Teaching a computer to understand the world like we do requires giving it a set of specific instructions to follow. This is called a computer algorithm. Except on a self-driving car, this has to happen in milliseconds so that the car can respond to a sudden event like a car slamming on its brakes. If you can figure out the correct steps, you can have a computer do just about anything we can, including driving a car. Here's a computer algorithm we wrote in the Python programming language to allow our self-driving electric go-kart to see the racetrack. So yeah, that's a basic idea of what the perception team does on Wisconsin Autonomous.
State estimation is critical for accurately using and combining sensor data about the vehicle and surrounding environment. In order to know where the car should go next, we have to know where we currently are and how we're moving. This is called the vehicle state. We use GPS sensors to measure position and an inertial measurement unit to measure linear and rotational accelerations. We also use a wheel speed encoder as an additional measurement of vehicle velocity. We then combine these measurements for a better overall state estimate by using a Kalman filter, an algorithm made famous by enabling the Apollo 11 lunar landing. In addition to the state, it's also very important to know where the car is relative to surrounding obstacles and driving boundaries. For this, we keep a map stored in memory of surrounding points of interest and update that map as we drive. We have experimented with occupancy grid methods we have made ourselves and packages available in ROS, a software framework we use. The combined state estimation and mapping process is known as simultaneous localization and mapping, or SLAM for short. Once we accurately compute the vehicle state, we then pass on the state and map data to the driving function software.
Hey everyone, my name is Evan Deutsch and I am in charge of the driving functions subteam for Wisconsin Autonomous. Our team focuses on writing the code that allows the car to race in competitions. We build numerous different types of algorithms. The three most common are called path planning, path following, and obstacle avoidance. Path planning requires us to use the boundaries of the track to find the best way for the car to drive through it. Path following uses the path that we planned with the path planning algorithm, as well as the current location of the car, to tell the car how to steer and how fast to go. Lastly, since we are writing our programs to allow the car to win races, we must also be able to avoid other obstacles on the track. These are what the obstacle avoidance algorithms are for. With these tools, we are able to put our car on any track and watch it race and avoid collisions.
My name is Ian Rue, and I am one of the team's software leads, as well as the software platform's team leader. The software platform's team develops and maintains the software infrastructure required by the rest of the team. This includes managing our software architecture, making sure we have the computing resources needed by each subteam, and managing communication with the vehicle. In addition, we work with the simulation environment used by the perception and driving functions teams to make sure the transition from simulation to real hardware is as seamless as possible. Off of the vehicle, we help ensure each subteam has access to the computing resources they need for the development, whether it is testing a controls algorithm in a simulation or using a GPU to train a machine learning model.
This is our power steering unit. It is mounted in line with the steering shaft and allows for both manual and autonomous driving modes. Here are our seat and our throttle and brake pedals. These will be used by the safety driver in case of an emergency. Our IMU sensor is located under the seat. This is used for state estimation. Here is our motor controller, which controls our DC electric motor. Our powertrain requires 48 volts to operate, and this is supplied by these two lead-acid batteries. Our auxiliary battery supplies the 12 volts necessary for computing and actuation. This is the chain and sprocket to beam rear axle drive, which takes the power from the motor and gets it to the rear axle. Here is the NVIDIA Jetson AGX Xavier, which is used for perception, state estimation, and controls processing. Here is the 0 to 5 volt autonomous throttle control and the CAN interface, which communicates with the actuators. These dual GNSS antenna are connected to the IMU and help supply data for state estimation. These two brake calipers are capable of both manual and autonomous braking. Our autonomous braking is powered by this brake-by-wire device. These two emergency stop buttons allow us to shut down power to the cart at any moment. Finally, our sensor tower to mount our stereo camera and LiDAR.
And last but certainly not least is operations, the glue connecting our full team. Operations oversees team financial statements, budget planning and cost reports, project management, team brand design and marketing, sponsor relations, media statements, and community outreach.